fun math stories, squaring the circle and pi. Since it's a special occasion, which is Pi Day, I'm joined with my best friend, Alexandria. Alex!
Yeah!
So, Alex, you know shapes, right?
Of course I know the shapes. Just look at this house. We've got triangles, rectangles, squares.
Yeah, there's a lot of shapes in this one house. But many natural items have smooth curves, like the sun
And the moon.
and the earth.
The earth's not flat.
I'm sorry, I meant the round earth, even water,
Oranges.
and even your eye.
I see that.
But Alexandria, do you know what a definition of the circle is?
No. Pause the video, please.
Let's figure it out.
We're back with a good definition.
Yeah, so in Euclid's famous book, The Elements, he described a circle as if you have a point and you have many other points surrounding it, and that the distance from the middle point to the outside points are always the same. It is a circle.
And if you take the measurement of the midpoint to the outer rope, that's called the radius. And if you take the rope and stretch it all the way across the circle, that's the circumference.
The circle is interesting because it is round, smooth, and symmetrical.
People also try to compare it with another common shape, the square. A circle comes inside of a square, in which case the square is obviously bigger. But we can also have a square inscribed in a circle.
Then the square is obviously smaller than the circle. But can we ever have a circle that's the same size as a square?
I don't know.
Let's find out!
It turns out that this is one of the most famous math puzzles derived from ancient mathematicians. They called it
Squaring the circle. Ancient Egyptians recorded this problem on Rhind papyrus.
In 1500 BC, over 3,500 years ago.
That's incredibly long ago.
Now let's take a look at how the ancient Egyptians solved this problem step by step.
What they first did is they took a square with side lengths of 9, and then they split it into 9 different squares, each 3 by 3.
Then they approximated the circle to be an octagon.
All they need to do now to find the octagon's area was to subtract the corners of the square from the square's area.
The octagon's area, which is 63, approximates to 64, which is the same area as the square with sides of 8.
What they found out is that a circle with a diameter of 9 has about the same area as a square with side lengths of 8.
As you can see, the ancient Egyptians made a pretty good approximation.
Yeah, and this was 3,500 years ago, long before our modern equipment. Over the next 3,000 years, many more mathematicians will try to find a better and great approximation for this squaring the circle problem.
Like Aristotle,
Archimedes,
Leonardo da Vinci,
and John Bernoulli. Mathematicians asked, the measurable item of the square is the side length A, and then we can easily find out the area of the square is its side square, or A squared.
but the only measurable part of the circle is the diameter.
How can we choose a diameter for the circle so that the area of the circle is the same as the square?
I don't know.
Let's find out!
We can fit a regular polygon into the circle, and as you increase the sides, it gradually looks more and more like a circle. Let's look at how Archimedes solved this problem.
Archimedes solved this problem by inscribing a hexagon into the circle.
Then, a hexagon is very special because you can fit 6 equilateral triangles in it.
That means that the side length of the hexagon is equal to the radius of the circle.
Exactly!
So, Archimedes wanted to increase the number of sides the polygon has in order to more approximately find the area of the circle.
He did this very intelligently, though, and doubled the number of polygons each time.
So, all he needed to do was find the side length of the new polygon, or to put in your perspective, find the side lengths of NP.
Yeah.
Now, let's first assume that the side length of the hexagon is 1.
In the special case of the equilateral triangle, if you split the angle, it creates two right-angled triangles.
This very special right triangle has degrees of 30, 60, and 90. The Pythagorean theorem to find out the length of OM is the square root of 3 divided by 2. Now we can easily find out the length of NP by subtracting the length of OM from the radius.
But there's another right triangle, NMP.
Yeah, and then we use the Pythagorean theorem a second time. And then we can easily find out the length of NP.
This process just keeps repeating and repeating.
You see, every time Archimedes used this method, he was able to double the polygon and find the side length of the new polygon.
He kept repeating this process and ended up with a 96-sided polygon.
We discussed before, a more and more sided polygon becomes more and more like a circle. Archimedes simply added all the sides of a many-sided polygon and approximated the circumference of a circle. What was even more amazing is that when Archimedes divided the circumference by the diameter, no matter how big the circle was, he would get a constant value. We now call this pi.
Archimedes ended up with a 96-sided polygon and set the basis for pi today, saying that it was between 3.1409 and 3.1429. Around 265 AD, the Chinese mathematician Liu Hui.
Whoa, you speak Chinese?
Yi Dian Dian.
Well, better than me. But anyways, Liu Hui used his own 96-sided polygon to find his own pi, or 3.141516, very close to the pi we use today.
But what is pi? What's its true value?
Well, Van Lindemann in the 19th century officially confirmed that pi is irrational.
Meaning that it goes on forever and ever with no repeating pattern. He not only approved, though, that it was irrational, but also transcendental.
A transcendental number is a number that is not the root of a non-zero polynomial with a finite degree and a positive coefficient. I really have no idea what that means, but I do know this basically indicates circle, because of the uniqueness of pi, is non-squareable.
So,
It's Mission Impossible!
Thank you all so much for watching our video. I hope you enjoyed it as much as we enjoyed making it.
And Happy Pi Day! Remember to subscribe, helps out a ton, and click that notification bell. We'll see you next time. Bye!